Welcome. Settle in. Let the pillow take the weight of your head and let your breathing slow to its own quiet rhythm. Tonight, we are going to learn about something you use every single day, probably without thinking about it. Something so ordinary that it has become invisible, and yet so extraordinary that it relies on one of the most famous theories in the history of science to work correctly. Tonight, we are going to learn exactly how GPS satellites use Einstein's theory of relativity to find your location. Every time you open a map on your phone, every time your ride-sharing app knows where you are, every time a delivery driver finds your house or an airplane navigates across the ocean, GPS is at work. The Global Positioning System. It is one of the most remarkable technologies humanity has ever built, and it works with an accuracy that would have seemed like magic a few decades ago. Your phone can determine your position on the surface of the Earth to within a few meters. Sometimes even less. But here is the thing that most people do not know. GPS would not work without Einstein's theory of relativity. Without the corrections that relativity provides, your GPS would drift by about 10 kilometers every single day. Within a week, your map would be useless. Within a month, your phone would think you were in a different city. The entire system depends on Einstein's insights about the nature of space and time, insights that he developed more than a century ago, long before anyone imagined a satellite navigation system. So tonight, we are going to take this apart, piece by piece. We are going to understand exactly how GPS works, why it needs relativity, and what Einstein figured out that makes it all possible. We will start with the basics and build up slowly, so there is nothing to worry about. Just listen. Let the ideas settle in at their own pace. And if you drift off to sleep before we finish, that is perfectly fine. The satellites will keep orbiting. The clocks will keep ticking. And your phone will still know where you are in the morning. Let us begin with the basics. What is GPS? The Global Positioning System is a network of satellites that orbit the Earth at an altitude of about 20,200 kilometers, roughly 12,500 miles above the surface. There are currently 31 operational GPS satellites, arranged in 6 orbital planes, so that at least 4 satellites are visible from virtually any point on Earth at any time. Each satellite completes one full orbit every 12 hours, traveling at about 14,000 kilometers per hour. Each of these satellites carries an extremely precise atomic clock and continuously broadcasts a signal that contains 2 pieces of information: the satellite's exact position in space at that moment, and the exact time the signal was sent. That is it. That is all the satellite does. It tells you where it is and what time it sent the message. Everything else, including figuring out where you are, is done by the receiver in your phone. The GPS satellites are maintained and operated by the United States Space Force. The system was originally developed for military use in the 1970s and 80s, and it became fully operational in 1995. It was opened to civilian use by President Reagan in 1983, after a Korean Airlines flight was shot down when it strayed into Soviet airspace, partly due to navigation errors. Since then, GPS has become one of the most widely used technologies in human history, embedded in everything from smartphones to farming equipment to financial trading systems. But how does knowing the position and time of a satellite help your phone figure out where you are? The answer is a beautiful piece of geometry that relies on the speed of light. When your phone receives a signal from a GPS satellite, it compares the time the signal was sent, which is encoded in the signal, with the time the signal was received, which is measured by the clock in your phone. The difference between these 2 times tells your phone how long the signal took to travel from the satellite to your phone. And since the signal travels at the speed of light, which is about 300,000 kilometers per second, your phone can calculate the distance between itself and the satellite. For example, if the signal took 0.067 seconds to travel from the satellite to your phone, then the distance is the speed of light multiplied by the travel time, which works out to about 20,000 kilometers. Your phone now knows that it is somewhere on the surface of a sphere centered on that satellite, with a radius of 20,000 kilometers. But a sphere is a big place. You could be anywhere on it. One satellite is not enough. Now imagine your phone receives a signal from a second satellite and calculates a different distance. Your phone is now on the surface of two spheres, one centered on each satellite. The intersection of two spheres is a circle. So your phone knows it is somewhere on that circle. Better, but still not precise enough. Add a third satellite. The intersection of three spheres is 2 points. And since one of those points is usually somewhere absurd, like deep inside the Earth or far out in space, your phone can eliminate it and determine your position from the other point. In practice, GPS uses a fourth satellite to account for timing errors in your phone's clock, which is far less precise than the atomic clocks on the satellites. The fourth satellite allows the system to solve for 4 unknowns simultaneously: your latitude, your longitude, your altitude, and the exact offset of your phone's clock from GPS time. This technique is called trilateration, and it is a beautiful example of how geometry and the speed of light can be combined to determine a position with remarkable accuracy. Let us pause and really appreciate the elegance of trilateration. It is essentially using spheres of known radius to pinpoint a location in 3-dimensional space. Each sphere is defined by the distance from your phone to a satellite, and the distance is determined by the travel time of a signal moving at the speed of light. The mathematics is the same mathematics that ancient Greek geometers used to study the intersections of circles and spheres, but applied with modern technology and breathtaking precision. Geometry, the oldest branch of mathematics, combined with the speed of light, the most fundamental constant in physics, gives us the ability to locate any object on the surface of the Earth to within a few meters. It is also worth understanding why 4 satellites are needed rather than 3. In theory, 3 satellites are enough to determine a position. But in practice, the clock in your phone is not an atomic clock. It is a cheap quartz crystal oscillator that might be off by several milliseconds, which would correspond to an error of hundreds of kilometers. By using a 4th satellite, the GPS receiver can treat the clock error as an additional unknown and solve for it along with your 3 coordinates. In practice, modern receivers often use 6, 8, or even 12 satellites simultaneously, using the extra measurements to improve accuracy and to cross-check for errors. But it all depends on one critical thing: the timing must be extraordinarily precise. Let us appreciate just how precise the timing needs to be. Light travels at about 300,000 kilometers per second. That means it covers about 300 meters in 1/1,000,000th of a second, 1 microsecond. If the clocks in the GPS system are off by just 1 microsecond, the calculated position will be wrong by about 300 meters. That is 3 football fields of error from a timing mistake of 1/1,000,000th of a second. To achieve the meter-level accuracy that GPS provides, the timing needs to be accurate to about 3 nanoseconds, 3 billionths of a second. At the speed of light, 3 nanoseconds corresponds to about 1 meter. So the clocks in the GPS system need to be accurate to within a few billionths of a second. This is an almost incomprehensible level of precision. A nanosecond is to a second what a second is to about 31 years. The GPS system requires this level of accuracy, sustained continuously, on satellites orbiting 20,000 kilometers above the Earth. This is why each GPS satellite carries atomic clocks. Atomic clocks measure time by counting the oscillations of atoms, specifically cesium or rubidium atoms, which vibrate at extremely precise and stable frequencies. A cesium atomic clock oscillates at exactly 9,192,631,770 times per second. By counting these oscillations, the clock can measure time with an accuracy of about 1 nanosecond per day. This frequency is so stable and so reproducible that it has been used to define the second itself since 1967. In a cesium atomic clock, a beam of cesium atoms is exposed to microwave radiation at a frequency close to this transition frequency. When the microwave frequency matches the cesium transition frequency exactly, the atoms absorb the radiation and change energy states. A detector measures how many atoms have changed states, and a feedback loop adjusts the microwave frequency to keep it locked to the transition frequency. The result is a clock that ticks at an extraordinarily stable rate, accurate to about 1 second in 30 million years. The newer generation of GPS satellites carries even more precise clocks, and on the ground, the GPS control stations use hydrogen maser clocks, accurate to about 1 second in 100 million years. These clocks are marvels of engineering. They are among the most precise instruments humanity has ever built. And they need to be, because the entire GPS system stands or falls on the accuracy of its timing. A tiny error in time becomes a large error in position, because light is so extraordinarily fast. The relationship between time and distance, mediated by the speed of light, is the foundation of the entire system. And this is exactly where Einstein enters the story. Because it turns out that time does not tick at the same rate everywhere. The rate at which a clock ticks depends on how fast it is moving and on how deep it sits in a gravitational field. And the GPS satellites are both moving fast and sitting in a different gravitational field than clocks on the ground. If we do not account for these effects, the GPS clocks will drift, and the system will become inaccurate within hours. The corrections come from two of Einstein's most famous theories, special relativity and general relativity. Let us start with special relativity. Einstein published this theory in 1905, when he was just 26 years old and working as a patent clerk in Bern, Switzerland. It is one of the most revolutionary ideas in the history of science, and it begins with a simple observation: the speed of light is the same for all observers, regardless of how they are moving. This sounds innocuous, but its consequences are profound. If the speed of light is the same for everyone, then something else has to give. And what gives is time. Einstein showed that time passes more slowly for objects that are moving relative to you. This is called time dilation. Here is an intuitive way to think about it. Imagine a clock made of two mirrors facing each other, with a beam of light bouncing back and forth between them. Each bounce of the light is one tick of the clock. Now imagine that this clock is moving sideways, at a very high speed. From your perspective, the light beam is no longer bouncing straight up and down. It is tracing a zigzag path, because the mirrors are moving sideways while the light bounces between them. The zigzag path is longer than the straight up and down path. But the speed of light is the same. So if the light has to travel a longer path at the same speed, it takes more time between each tick. The moving clock ticks more slowly. This is not something wrong with the clock. It is something real about the nature of time. Time itself passes more slowly for objects that are moving. And this has been directly measured. In 1971, physicists Joseph Haefel and Richard Keating put atomic clocks on commercial airplanes and flew them around the world. When they compared the airplane clocks to identical clocks that had stayed on the ground, they found that the airplane clocks had ticked slightly less. The difference was tiny, just a few hundred nanoseconds, but it was exactly the amount predicted by Einstein's theory. The Haefel-Keating experiment is worth dwelling on for a moment. The physicists flew eastward around the world and then westward. The eastward flying clocks lost time relative to the ground clocks, because they were moving faster. The Earth's rotation adds to the airplane's speed when flying east. The westward flying clocks gained time, because they were effectively moving slower relative to the center of the Earth. Both results matched Einstein's predictions to within experimental error. Time is not fixed. It is flexible. It bends and stretches depending on how you move through space. Muon particles provide another vivid confirmation of time dilation. Muons are subatomic particles created when cosmic rays hit the upper atmosphere, about 15 kilometers above the surface. Muons are unstable and decay very quickly, with a half-life of about 2.2 microseconds. If you do the math, a muon traveling at nearly the speed of light should only travel about 660 meters before it decays. It should never reach the ground. And yet, muons are detected at the Earth's surface all the time. The reason is time dilation. From our perspective, the muon's internal clock is running slowly because it is moving so fast. The muon experiences only 2.2 microseconds of time, but from our perspective, much more time passes, enough for the muon to travel the full 15 kilometers to the surface. Now let us apply this to GPS. The GPS satellites orbit the Earth at a speed of about 3.9 kilometers per second, or about 14,000 kilometers per hour. That is fast by human standards, but it is only about 13,000% of the speed of light. So the time dilation effect is small, but it is not zero. According to special relativity, the clocks on the GPS satellites tick slightly more slowly than clocks on the ground, because they are moving. The difference is about 7 microseconds per day. That might sound trivial, but 1 microsecond of timing error corresponds to about 300 meters of position error. 7 microseconds per day would mean an error of about 2.1 kilometers per day, accumulating steadily. But special relativity is only half the story. The other half comes from general relativity, which Einstein published in 1915. General relativity is a theory of gravity, and it says something even stranger than special relativity. Gravity is not a force that pulls objects together. Gravity is a curvature of spacetime caused by the presence of mass and energy. Objects do not fall because a force is pulling them. They fall because they are following the curved geometry of spacetime around a massive object like the Earth. And one of the consequences of this curvature is that time passes at different rates depending on how deep you are in a gravitational field. The deeper you are, the more spacetime is curved, and the more slowly time passes. This is called gravitational time dilation. Imagine you are standing at the base of a very tall tower. Your friend is standing at the top. You both have identical atomic clocks. General relativity says that your clock, at the base, will tick slightly more slowly than your friend's clock at the top. Not because there is anything wrong with either clock, but because time itself passes more slowly in a stronger gravitational field. This effect has been directly measured many times. In 1959, physicists Robert Pound and Glenn Rebka measured it at Harvard University. And in 2010, scientists demonstrated that this effect is measurable even over a height difference of just 33 centimeters. Raise a clock by 1 foot, and it ticks faster. There is a beautiful way to understand why gravity affects time. In general relativity, gravity is not a force. It is a curvature of space-time. And space-time includes time as well as space. When mass curves space-time, it curves the time dimension along with the spatial dimensions. Clocks in different gravitational fields are literally moving through time at different rates. This has a practical consequence that is easy to state but hard to fully absorb. If you live on the ground floor of a tall building and your neighbor lives on the top floor, your neighbor ages slightly faster than you do. The difference is far too small to notice, fractions of a nanosecond per year, but it is real and measurable with modern atomic clocks. Time is not a uniform, universal quantity ticking away at the same rate for everyone. It is a local quantity, dependent on your speed and your position in a gravitational field. This was Einstein's great insight, and it is the insight that makes GPS possible. Now let us apply this to GPS. The satellites orbit at an altitude of about 20,200 kilometers. At that altitude, the gravitational field is significantly weaker than at the surface. This means that time passes faster for the satellite clocks than for clocks on the ground. The effect of general relativity makes the satellite clocks tick faster by about 45 microseconds per day. So we have two effects pulling in opposite directions. Special relativity makes the satellite clocks tick slower by about 7 microseconds per day because of their speed. general relativity makes them tick faster by about 45 microseconds per day because of the weaker gravity. The net effect is that the satellite clocks tick faster than ground clocks by about 38 microseconds per day. 38 microseconds per day. That is the total relativistic correction that GPS needs. It sounds tiny. 38 millionths of a second. But at the speed of light, 38 microseconds corresponds to about 11.4 kilometers of error per day. Without this correction, GPS would accumulate an error of more than 11 kilometers every single day. Within a week, it would be off by 80 kilometers. Within a month, 340 kilometers. The system would be completely useless. So the GPS system has to account for relativity. And it does, in a beautifully simple way. Before a GPS satellite is launched, the frequency of its atomic clock is adjusted slightly. The clocks are designed to tick at a frequency of 10.23 MHz. But before launch, they are set to tick at a slightly lower frequency, 10.22999995 for 3 MHz. This tiny adjustment exactly compensates for the 38 microsecond per day drift caused by relativity. When the satellite is in orbit, the combined effects of special and general relativity speed up the clock by exactly the amount needed to bring its tick rate back to the correct frequency as seen from the ground. But the story does not end there. There is a third relativistic effect that GPS must account for, called the Sagnac effect. Because the Earth rotates, a signal traveling from a satellite to a receiver on the surface is affected by the motion of the receiver during the time the signal is in transit. The receiver moves east, toward the incoming signal from some satellites and away from others, and this motion introduces a timing error that must be corrected. The Sagnac correction is smaller than the gravitational and velocity corrections, typically less than 100 nanoseconds, but it is still significant enough to affect the accuracy of the position calculation. There are also periodic relativistic effects caused by the eccentricity of the satellite orbits. GPS satellites do not orbit in perfect circles. Their orbits are slightly elliptical, which means their altitude and speed change slightly over the course of each 12-hour orbit. When the satellite is closer to Earth, it moves faster and the gravitational field is stronger. When it is farther from Earth, it moves slower and the gravitational field is weaker. These variations cause the relativistic time correction to oscillate with an amplitude of about 46 nanoseconds. All told, the relativistic corrections applied to GPS involve special relativity, general relativity, the Sagnac effect, and orbital eccentricity. Together, they constitute one of the most complete and practical applications of Einstein's theories in existence. This is one of the most elegant and practical applications of Einstein's theories. A theory developed by a patent clerk in 1905 and refined over the following decade, a theory about the fundamental nature of space and time, turns out to be essential for the navigation system in your pocket. Without Einstein, your phone would not know where you are. So now let us put it all together. You open a map on your phone. Your phone's GPS receiver begins listening for signals from satellites broadcasting on microwave frequencies. Each satellite broadcasts a unique code that allows your phone to distinguish between signals from different satellites. Your phone generates its own copy of each satellite's code and compares it to the incoming signal. By sliding its copy forward and backward in time until it matches, the phone measures the travel time of the signal. The travel time, multiplied by the speed of light, gives the distance to the satellite. By combining distances from at least 4 satellites, the phone solves for your latitude, longitude, altitude, and clock error. The mathematics involved is not trivial. Your phone is solving a system of nonlinear equations in real time, typically converging within a few milliseconds. It is doing this while simultaneously correcting for relativistic effects, ionospheric delays, tropospheric delays, multipath effects, and errors in the satellite's reported position. All of this happens in the tiny GPS chip inside your phone, a chip that costs a few dollars and uses a fraction of a watt of power. It is one of the most impressive feats of engineering in human history. GPS is not the only satellite navigation system in the world. Russia operates GLONASS, with 24 satellites. The European Union operates Galileo, with 30 satellites. China operates Beidou, with 35 satellites. All of these systems work on the same basic principle, and all of them require relativistic corrections. Modern smartphones use signals from multiple constellations simultaneously, sometimes receiving from 20 or 30 satellites at once. The laws of nature do not respect national borders. Time dilation works the same way everywhere. Physics is the same everywhere, and satellite navigation is proof of that. The golden color of gold is a relativistic effect. The electrons in gold atoms move so fast that relativistic effects change their energy levels, shifting the frequency of light that gold absorbs. Without relativity, gold would look silvery white. Lead-acid batteries also depend partly on relativity. Particle accelerators like the Large Hadron Collider rely on relativity constantly. Einstein's theories are not abstract curiosities. They are woven into the fabric of modern technology. In 1905, Einstein was 26 years old, working as a patent clerk in Bern, Switzerland. In that single miraculous year, he published 4 papers that changed the world. Special relativity came from a thought experiment about riding alongside a beam of light. It took him another 10 years to extend his theory to include gravity. General relativity was confirmed in 1919 when Arthur Eddington measured the bending of starlight around the sun during a solar eclipse. But for decades, relativity was considered purely theoretical. It was only with atomic clocks and satellite navigation that it became a practical engineering concern. From a thought experiment about riding a beam of light to the navigation system in your pocket. From the patent office in Bern to the satellites orbiting 20,000 kilometers above your head. It is a reminder that pure curiosity, the simple desire to understand how the universe works, can lead to the most practical and far-reaching consequences. The same laws of physics that govern the expansion of the universe also govern the tiny microwave signals traveling from a satellite to your phone. There is one set of rules, and they apply everywhere, at every scale. The universe is unified. It is coherent. It makes sense. And because it makes sense, we can navigate it. Let us think more carefully about what the speed of light means for GPS. The speed of light in a vacuum is exactly 299,792,458 meters per second. This is not an approximate number. It is exact, because since 1983, the meter has been defined in terms of the speed of light. 1 meter is the distance light travels in 299,792,458th of a second. So when GPS uses the speed of light to convert time into distance, it is using the most fundamental measurement standard in all of physics. The distance from a satellite to your phone is literally defined by the time it takes light to cross it. This means that GPS is, in a very real sense, a device for measuring space-time itself. It measures time with atomic clocks and converts that time into distance using the speed of light. And when it corrects for relativistic effects, it is directly measuring the curvature of space-time around the Earth. Every time your phone calculates your position, it is performing a tiny experiment in general relativity. It is sensing the warping of space and time caused by the mass of the planet beneath your feet. Your phone is a space-time sensor. You carry a general relativity detector in your pocket. There is a deeper point here that is worth contemplating as you lie in the dark. The fact that GPS works at all is proof that the universe obeys mathematical laws. The equations of special and general relativity, written down by Einstein over a century ago, predict with extraordinary precision how clocks behave on satellites orbiting the Earth. The predictions match the observations to the limits of our ability to measure. This agreement between theory and experiment is not guaranteed. There is no logical reason why the universe should obey mathematical laws at all, let alone laws that a human being can discover and write down. And yet it does. The universe is comprehensible. It is lawful. It is predictable. And that predictability is what makes technology possible. Every time you use GPS, you are witnessing a conversation between human intelligence and the deep structure of reality. Einstein figured out the rules. Engineers built machines that exploit the rules. And the universe cooperates, obeying those rules with flawless consistency every microsecond of every day, in every corner of the globe. There is something deeply reassuring about that. The universe is reliable. It keeps its promises. The laws of physics that held yesterday will hold tomorrow. The speed of light will not change overnight. Time dilation will not suddenly stop working. The clocks on the satellites will continue to tick exactly as Einstein predicted. You can rely on the universe to be consistent, and because of that, you can rely on GPS to find your way. Let us talk about how GPS handles the problem of the ionosphere in a bit more detail, because it is a fascinating example of using physics to solve a practical problem. The ionosphere is a layer of the Earth's atmosphere that extends from about 60 kilometers to about 1,000 kilometers above the surface. It is called the ionosphere because it contains a high concentration of ions and free electrons, produced by ultraviolet radiation from the sun that strips electrons from atmospheric molecules. When a GPS signal passes through the ionosphere, the free electrons interact with the electromagnetic wave, causing it to slow down. The amount of slowing depends on the density of free electrons, which varies with time of day. It is much higher during the day than at night, with the season, with the 11-year solar cycle, and with unpredictable events like solar flares and geomagnetic storms. A large solar flare can dramatically increase the electron density of the ionosphere, introducing GPS errors of 10 meters or more. Dual-frequency GPS receivers can measure the ionospheric delay directly by comparing the arrival times of signals on two different frequencies. This works because the ionospheric delay is frequency-dependent. Lower frequency signals are delayed more than higher frequency signals. By measuring the difference in arrival times, the receiver can calculate the electron density along the signal path and correct for the delay. This is one of the reasons why the most precise GPS applications use dual-frequency receivers. Single-frequency receivers, like those in most smartphones, rely on a mathematical model of the ionosphere called the Klobuchar model, which predicts the delay based on time of day and location. This model corrects for about 50 to 60% of the ionospheric error, which is good enough for most civilian applications but not for the highest precision work. The troposphere, the lowest layer of the atmosphere where weather occurs, also delays GPS signals, but for different reasons. In the troposphere, the delay is caused by the refraction of the signal as it passes through air of varying density, temperature, and humidity. The dry component of the tropospheric delay, caused by the density of the air itself, is relatively constant and can be modeled accurately. The wet component, caused by water vapor, is much more variable and harder to predict. On a humid day, the wet tropospheric delay can add several centimeters of error to a GPS position. Advanced GPS receivers use atmospheric models and real-time weather data to correct for both components. The level of engineering required to make all of these corrections, relativistic, ionospheric, tropospheric, orbital, and multipath, simultaneously and in real time, on a chip smaller than your fingernail, is truly staggering. It is easy to take GPS for granted because it works so seamlessly. You open your phone, and there is a blue dot on the map showing where you are. It seems simple. But behind that blue dot is one of the most sophisticated engineering achievements in human history, a system that weaves together quantum mechanics, general relativity, orbital mechanics, signal processing, atmospheric physics, and advanced mathematics into a seamless whole. It is a monument to human ingenuity, and it is in your pocket right now. The history of navigation helps us appreciate how revolutionary GPS truly is. For most of human history, finding your exact position on the surface of the Earth was extraordinarily difficult. On land, you could use landmarks and roads. But at sea, where there are no landmarks, navigation was a matter of life and death. Ancient sailors navigated by the stars, using the angle of the North Star above the horizon to estimate their latitude, their north-south position. But longitude, the east-west position, was far harder to determine. The problem of longitude plagued navigators for centuries and led to countless shipwrecks, lost cargoes, and thousands of deaths. Entire fleets were lost because they did not know where they were. The reason longitude was so difficult is that it requires knowing the exact time at a reference location and comparing it to the local time. The difference in time, multiplied by 15 degrees per hour, gives you the difference in longitude. But keeping accurate time at sea, on a rolling, pitching ship, in conditions of extreme temperature and humidity, was nearly impossible with the pendulum clocks of the 17th and 18th centuries. The British government offered a prize of £20,000, an enormous fortune at the time, to anyone who could solve the longitude problem. The prize attracted the attention of astronomers, mathematicians, and instrument makers from across Europe. The longitude problem was eventually solved in the 18th century by John Harrison, a self-taught English clockmaker who spent decades building the first marine chronometer. Harrison's fourth design, known as H4, was a masterpiece of mechanical engineering, accurate to about 1/3 of a second per day. By comparing the local time, determined by the position of the sun, with the time at Greenwich kept by the chronometer, a navigator could calculate the difference in longitude. Today, GPS atomic clocks are accurate to about 1/1000th of a second per day, an improvement of about 300 million times over Harrison's masterpiece. The principle is exactly the same, using accurate time to determine position, but the precision has improved by a factor that is almost impossible to comprehend. Harrison's story is one of the most compelling in the history of science and technology. He was not a wealthy man. He was not a university-educated scientist. He was a carpenter's son from Yorkshire who taught himself clockmaking. He spent over 30 years of his life building and refining his marine chronometers, facing constant skepticism from the scientific establishment, who believed the longitude problem could only be solved through astronomical observations, not through mechanical clocks. Harrison persevered, driven by the conviction that a sufficiently accurate clock could solve the problem that had claimed so many lives at sea. And he was right. Harrison's first attempt, H1, was a massive machine weighing over 30 kilograms, designed to resist the effects of motion, temperature, and humidity on a ship. It worked well but was too large and complex for practical use. H2 and H3 followed, each an improvement over the last, but Harrison was never satisfied. Finally, late in life, he produced H4, a watch-sized chronometer of exquisite beauty and precision. H4 was tested on a voyage to Jamaica in 1761 and proved accurate to within 5 seconds over an 81-day journey. It easily met the requirements for the longitude prize, but Harrison had to fight for years to receive his full reward, which was eventually granted only after the personal intervention of King George III. The connection between Harrison's struggle and the GPS system is deeper than you might think. Harrison understood something that many of his contemporaries did not, that accurate time is the key to accurate navigation. This same insight underpins GPS. The technology has changed beyond recognition, from brass gears and balance springs to cesium atoms and microwave radiation, but the fundamental principle is identical. Time and position are linked by the speed of a signal, whether that signal is the position of the sun in the sky or a microwave pulse from a satellite traveling at the speed of light. Navigation has always been about time. It always will be. Let us also take a moment to think about the satellites themselves as physical objects, because there is something remarkable about them that most people do not consider. Each GPS satellite weighs about 2,000 kilograms, roughly the weight of a large car. It spans about 5 meters across with its solar panels extended, drawing about 700 watts of power, similar to the power consumption of a small microwave oven. The satellites are designed to last about 12 years, though many have exceeded their design life and continue to operate for 15 or 20 years. Inside each satellite, in addition to the atomic clocks, there are computers that store and broadcast the navigation messages, transmitters that send the signals on multiple frequencies, receivers that pick up commands from the ground control stations, and attitude control systems that keep the satellite oriented correctly, with its antennas pointing toward the Earth and its solar panels pointing toward the Sun. Each satellite also carries small thrusters that can be used to adjust its orbit slightly, keeping it in its designated position. The satellites orbit in what is called a medium Earth orbit, at an altitude of about 20,200 kilometers. This altitude was chosen carefully. Higher orbits would mean fewer satellites could cover the entire Earth, requiring more satellites to maintain coverage. Lower orbits would mean the satellites would move across the sky too quickly, making it harder for receivers to track them. At the chosen altitude, each satellite is visible from a given point on the Earth for several hours at a time, and the constellation of 31 satellites provides continuous coverage of the entire globe, including the poles, the oceans, and the most remote areas of land. The signals broadcast by GPS satellites are remarkably weak by the time they reach the ground. The satellite transmits at a power of about 20 watts, similar to a dim light bulb. By the time that signal has traveled 20,000 kilometers through space and the atmosphere, it has spread out over an enormous area, and the power received by your phone's antenna is about 100 quintillionth of a watt. That is 10 to the power of -16 watts. It is an astonishingly faint signal, far weaker than the background noise of the radio environment. The fact that your phone can detect and decode this signal is a testament to the sophistication of modern signal processing algorithms, which can extract meaningful information from signals buried deep in noise. Think about that for a moment as you drift toward sleep. Right now, signals weaker than the faintest whisper, transmitted from satellites the size of a car, 20,000 kilometers above your head, are passing through the walls of your room, through the air around you, through your body, carrying the precise time measured by atoms vibrating 9 billion times per second, corrected for the curvature of space-time predicted by a theory written down over a century ago by a patent clerk who had trouble finding a teaching job. And if you turned on your phone and opened a map, all of that, the satellites, the atomic clocks, the relativity, the signal processing, would come together in a fraction of a second to place a little blue dot on the screen showing exactly where you are. It is one of the most extraordinary things human beings have ever accomplished. And it happens billions of times a day, all around the world, without anyone giving it a second thought. There is something poetic about this connection between Harrison's chronometer and the GPS satellite. Both solve the same fundamental problem using the same fundamental insight, that accurate time can be converted into accurate position. Harrison spent his entire adult life perfecting a clock for this purpose. Today, we carry devices in our pockets that solve the same problem with an accuracy Harrison could not have imagined, using clocks so precise that they must account for the curvature of space-time itself. The thread that connects Harrison's workshop to a GPS satellite is the thread of precision timekeeping. And that thread leads directly through Einstein. The GPS ground control segment plays a crucial role in keeping the system accurate. It consists of a master control station at Schriever Space Force Base in Colorado, an alternate master control station, 12 command and control antennas, and 16 monitoring stations distributed around the world, from Hawaii to Ascension Island to Diego Garcia to Kwajalein. The monitoring stations continuously track the GPS satellites, measuring their signals and comparing the satellite clocks to highly precise ground-based hydrogen maser clocks. These measurements are used to calculate precise updates to each satellite's orbit and clock parameters, which are then uploaded to the satellites at least once per day. This continuous monitoring and correction process is essential for maintaining accuracy. Even atomic clocks drift slightly over time, and satellite orbits are affected by tiny perturbations from the gravitational pull of the Moon and Sun, from solar radiation pressure, which gently pushes on the satellite's solar panels, and from the non-uniform distribution of mass within the Earth. The ground control segment detects and corrects for all of these effects, keeping the system accurate to within a few nanoseconds. Without this ground infrastructure, the GPS satellites would gradually drift out of synchronization, and the system's accuracy would degrade within days. The precision of GPS has enabled technologies that extend far beyond navigation. High-frequency financial trading systems use GPS timing to synchronize transactions across different stock exchanges with nanosecond precision. A few nanoseconds of advantage in timing can translate into millions of dollars of profit, so the financial industry has become one of the most demanding users of GPS timing. Power grids use GPS timing to synchronize the phases of alternating current across vast networks, ensuring that electricity flows smoothly from one region to another. Seismologists use GPS to measure the tiny movements of the Earth's tectonic plates, detecting shifts of just a few millimeters per year, information that is essential for understanding earthquakes and volcanic activity. Farmers use GPS-guided tractors to plow fields with centimeter-level precision, reducing overlap, saving fuel, and increasing yields. Airlines use GPS for approach and landing guidance. Search and rescue teams use GPS to coordinate operations in remote areas. Scientists use GPS to study the atmosphere, measuring the delay of GPS signals as they pass through the ionosphere and troposphere to map the distribution of water vapor and charged particles in the atmosphere. The applications of GPS extend into almost every area of modern life, and all of it, every single application, depends on the relativistic corrections that keep the atomic clock synchronized. There is one more aspect of GPS worth discussing before we wind down, and it has to do with the future. The next generation of GPS satellites, known as GPS-3, is already being deployed. These satellites carry more accurate atomic clocks, broadcast signals on additional frequencies, and include features designed to improve accuracy and resistance to jamming. The most advanced GPS-3 satellites can achieve positioning accuracy of about half a meter for military users and about 1 meter for civilians, a significant improvement over the current generation. Beyond GPS-3, there are even more ambitious plans. The European Galileo system is designed to provide accuracy of about 1 meter, with a high-accuracy service that can achieve 10 centimeters. Future systems may use optical atomic clocks, which are even more precise than the microwave-based clocks used today, potentially achieving accuracy of 1 centimeter or less. And there is growing interest in developing navigation systems that work indoors, underground, and underwater environments where GPS signals cannot penetrate. These systems may use different technologies, such as ultra-wideband radio, LiDAR, or inertial navigation, but the fundamental challenge is the same, using accurate timing and the speed of electromagnetic radiation to determine position. The story of GPS is really the story of humanity's relationship with time. From ancient sundials to medieval water clocks to Harrison's chronometer to cesium atomic clocks to the relativistic corrections that keep GPS accurate, the history of navigation is the history of our ability to measure time with ever-increasing precision. And at the heart of that story is a discovery that no one expected, that time itself is not absolute. That it bends and stretches and flows at different rates depending on how you move and where you are. That the universe is stranger and more beautiful than anyone imagined until a young patent clerk in Bern figured it out. Right now, as you lie here, 31 GPS satellites are circling the Earth, each one carrying clocks that tick with an accuracy of billionths of a second. Each one broadcasting its position and time into the void, orbiting the Earth once every 12 hours, 20,000 kilometers above the oceans and the mountains and the cities and you. And on each of those satellites, the clocks have been adjusted by a tiny amount to account for the fact that time passes differently in orbit than it does on the ground. That tiny adjustment is the fingerprint of Einstein's genius on one of the most useful technologies in human history. The history of navigation is worth a brief digression because it helps us appreciate just how revolutionary GPS is. For most of human history, finding your position on the Earth was extraordinarily difficult. On land, you could use landmarks, rivers, and roads. But at sea, where there are no landmarks, navigation was a matter of life and death. Ancient sailors navigated by the stars, using the positions of celestial objects to estimate their latitude. But longitude, the east-west position, was far harder to determine. The problem of longitude plagued navigators for centuries and led to countless shipwrecks and deaths. The longitude problem was eventually solved in the 18th century by John Harrison, a self-taught English clockmaker who built the first marine chronometer, a clock accurate enough to keep time at sea. By comparing the local time, determined by the position of the sun, with the time at a reference location, kept by the chronometer, a navigator could calculate the difference in longitude. Harrison's clock was accurate to about 1/5 of a second per day, which was revolutionary for the time. Today, GPS atomic clocks are accurate to about 1/1000th of a second per day, an improvement of about 200 million times. The principle is the same, using accurate time to determine position, but the precision has improved by a factor that is almost impossible to comprehend. There is something poetic about this connection. The problem that plagued sailors for centuries, the problem of knowing where you are on the surface of the Earth, has been solved so completely by GPS that we take it for granted. We can determine our position to within a few meters, anywhere on Earth, at any time, using a device that fits in our pocket. This would have seemed like the purest fantasy to the navigators who risked their lives crossing the Atlantic or the Pacific with nothing but a sextant and a chronometer. Let us also consider how the GPS ground control segment works, because it plays a crucial role in keeping the system accurate. The GPS ground control segment consists of a master control station at Schriever Space Force Base in Colorado, plus a network of monitoring stations and ground antennas distributed around the world. The monitoring stations continuously track the GPS satellites, measuring their signals and comparing the satellite clocks to the highly precise ground clocks. These measurements are used to calculate precise updates to each satellite's orbit and clock parameters, which are then uploaded to the satellites twice a day. This continuous monitoring and correction process is essential for maintaining the accuracy of the system. Even atomic clocks drift slightly over time, and satellite orbits are affected by tiny perturbations from the gravitational pull of the Moon and Sun, from solar radiation pressure, and from the non-uniform distribution of mass within the Earth. The ground control segment detects and corrects for all of these effects, keeping the system accurate to within a few nanoseconds. There is another fascinating aspect of GPS that is worth exploring. The system is designed to be resistant to jamming and interference. Military GPS signals are encrypted and broadcast on additional frequencies that civilian receivers cannot access. These encrypted signals provide higher accuracy and are much harder to disrupt. In recent years, GPS jamming and spoofing, in which fake GPS signals are broadcast to confuse receivers, have become growing concerns, particularly in conflict zones and near certain national borders. This has led to increased interest in developing more robust navigation systems and in using multiple satellite constellations simultaneously for added security. The precision of GPS has also enabled technologies that most people never think about. High-frequency financial trading systems use GPS timing to synchronize transactions across different exchanges with nanosecond precision. Power grids use GPS timing to synchronize the phases of alternating current across vast networks. Seismologists use GPS to measure the tiny movements of the Earth's tectonic plates, detecting shifts of just a few millimeters per year. Farmers use GPS-guided tractors to plow fields with centimeter-level precision, reducing waste and increasing yields. The applications of GPS extend far beyond navigation, into fields that its original designers never imagined. And all of it, every single application, depends on the relativistic corrections that keep the atomic clock synchronized. Without Einstein, none of it works. The financial trades would be mistimed. The power grids would lose synchronization. The seismological measurements would be meaningless. The tractors would plow crooked furrows. Relativity is not just a theoretical curiosity. It is the invisible foundation on which a vast infrastructure of modern technology rests. Right now, as you lie here, 31 GPS satellites are circling the Earth, each one carrying clocks that tick with an accuracy of billionths of a second. Each one broadcasting its position and time into the void, orbiting the Earth once every 12 hours, 20,000 kilometers above the oceans and the mountains and the cities and you. And on each of those satellites, the clocks have been adjusted by a tiny amount to account for the fact that time passes differently in orbit than it does on the ground. That tiny adjustment is the fingerprint of Einstein's genius on one of the most useful technologies in human history. Think about the satellites above you right now. They are moving at 14,000 kilometers per hour, but from their perspective, they are simply floating in space, weightless, following the curve of space-time around the Earth. Each one is a small metal box, no bigger than a car, covered in solar panels, orbiting in the silence of space. Inside each one, cesium atoms are vibrating 9 billion times per second, keeping time with an accuracy that no human sense could detect. And from each one, a radio signal is streaming downward at the speed of light, carrying two simple pieces of information: where the satellite is, and what time it is. Those signals are passing through you right now. Through the walls of your room, through your blanket, through your body. They are invisible and undetectable without a receiver, but they are there. The air around you is filled with signals from dozens of satellites, each one stamped with the time from an atomic clock corrected for the curvature of space-time. You are surrounded by relativity. You are immersed in it. It is as real and as present as the air you breathe. Let us consider one more remarkable thing about GPS before we close. The system works in all weather conditions, in rain and snow and fog, in the blazing heat of the desert and the bitter cold of the Arctic. GPS signals pass through clouds and precipitation with almost no attenuation, unlike visible light, which is blocked by clouds, or infrared radiation, which is absorbed by water vapor. This is because GPS uses microwave frequencies, which interact very weakly with water droplets and ice crystals. The same property that allows microwave ovens to heat food, the interaction of microwaves with water molecules, means that GPS signals pass through rain clouds with only minimal scattering. A thunderstorm that grounds airplanes and blinds radar systems has almost no effect on GPS accuracy. GPS also works equally well during the day and at night, obviously, since it does not depend on sunlight. It works at the poles, where magnetic compasses become unreliable because the magnetic field lines point nearly straight down. It works in the middle of the ocean, where there are no landmarks and no cell towers. It works on mountaintops and in valleys, in forests and on open plains. The only places GPS does not work well are deep inside buildings, underground, and underwater, where the weak satellite signals cannot penetrate. For these environments, other positioning technologies, such as Wi-Fi-based positioning, Bluetooth beacons, inertial navigation, and acoustic positioning, are used instead. The robustness of GPS is remarkable when you consider how fragile the system might seem. The signals are incredibly weak. The satellites are moving at 14,000 kilometers per hour. The clocks must maintain nanosecond accuracy over months. The orbits are perturbed by gravitational forces from the Sun and Moon. The signals pass through a turbulent atmosphere. And yet the system works day in and day out, year after year, providing billions of position fixes every day with meter-level accuracy. This reliability is a testament to the care and ingenuity that went into the system's design, and to the fundamental reliability of the laws of physics on which it is built. There is something else worth reflecting on. GPS is free. Anyone with a GPS receiver can use the system at no charge. There is no subscription fee, no per-use cost, no account to create. The United States government pays about $2 billion per year to maintain and operate the GPS constellation, and the signals are available to anyone, anywhere on Earth, for free. This decision, to make GPS freely available to the world, has had an enormous economic impact. Studies have estimated that GPS contributes over $300 billion per year to the United States economy alone, and trillions of dollars globally. The return on investment is staggering, one of the most successful examples of public investment in technology in history. And GPS continues to evolve. The newest GPS-3 satellites, the first of which was launched in 2018, carry more powerful and more accurate signals, better atomic clocks, and improved resistance to jamming and interference. Future upgrades will add new civilian signals on additional frequencies, allowing dual-frequency positioning for consumer devices, which will dramatically improve accuracy and reliability. Within the next decade, it is likely that your phone will be able to determine your position to within 30 centimeters or less, using signals from multiple satellite constellations, corrected not only for relativity but for the most subtle atmospheric and environmental effects. And all of it will continue to depend on the insights of a young man who, in 1905, realized that the speed of light is the same for all observers, and that time is not the fixed, universal quantity that everyone had assumed. Einstein could not have imagined GPS. He was thinking about the fundamental nature of the universe, about the deepest questions of space and time and gravity and light. But his answers to those questions turned out to be essential for a technology that has transformed the way billions of people live, work, and travel. There is a lesson in that. The most practical discoveries often come from the most impractical seeming questions. The most useful knowledge often emerges from the purest curiosity. And the deepest truths about the universe often turn out to have the most everyday applications. Your phone knows where you are because atoms vibrate at precise frequencies. Because light travels at a constant speed. Because time is not absolute but depends on motion and gravity. Because a young man in a patent office asked a strange question about what it would be like to ride a beam of light, and followed that question wherever it led, even when it led to conclusions that seemed impossible. That is the beauty of physics. Simple questions leading to profound answers. Abstract theories leading to practical technologies. Curiosity leading to understanding. Understanding leading to power. The power to know where you are on the surface of a small planet, orbiting an ordinary star, in a vast and mysterious cosmos. Let that thought settle over you like a blanket. You know where you are. Not just in the GPS sense. You are here. On Earth. Under the stars. Surrounded by invisible signals carrying information about space and time. Connected, through physics, to the deepest truths about reality. And now it is time to rest. Let the satellites do their work. Let the clocks tick. Let the signals travel through the night at the speed of light. You do not need to navigate anywhere right now. You just need to be here. Warm. Safe. Still. Close your eyes. Let the equations dissolve. Let the numbers fade. Let everything grow quiet and soft and slow. The universe knows exactly where you are. And right now, that is exactly where you need to be. Good night.